Let's take a little bit deeper look at this average normal stress and look at some examples. So the average normal stress, we said again, normal stress is represented by the Greek letter sigma, equals the normal force of our internal forces within that body, the normal force over the cross-sectional area. So, let's say we have maybe some rod here that's axially loaded, right? So there's some force, some normal force through that rod. Maybe there, it's axially loaded and in some way F on the outside. We cut through. This is the normal force we see inside. And so we'll use this normal force and this cross-sectional area A to calculate what the average stress is, right? And we say average normal stress just because this isn't a distributed load. It's not perfectly normal. We don't have the exact same force in every single spot on this surface here, but we can kind of average it out. We can say, okay, this force is working over this cross-sectional area, even though if it might be slightly stronger in some places, slightly weaker in some places, we say it's going to average out to be this normal force over the area. Otherwise, we would do like some limits and some calculus to get a little bit more of an integrated type answer, but for our purposes, this average normal stress is going to work well for us right now. So this average normal stress, again, just the normal force over the area. So let's take a look at a pretty basic example of this. Here I've got an I-beam cross-section, and we want to determine the average normal stress in this cross-section. It's got this 15 kip applied load on it. And so again, even though this 15 kip is a concentrated force, it's located in one spot, we're doing the average normal stress, so it's just going to be over that whole cross-sectional area here. So we know our load, right, and our normal stress equals the normal force over the area. So in this case, they gave us the force here is 15 kips. And then we'll need to find our cross-sectional area, which luckily is pretty simple. We have this 1/4 section here. So 1 inch times 4 inches is going to be 4 square inches. Plus this is another 4/1 cross-sectional area. So another 4 square inches. And then finally another 4/1. So 4 plus 4 plus 4 gives us 12 square inches. So now we just plug and chug that, and that gives us 15 over 12 is 1.25 KSI, kips per square inch, is our normal force, right? Pretty straightforward equation, pretty straightforward application. Let's look at a couple of other examples where we might use this. In this example, we have this kind of funky looking bar that has all of this axial loading along it, right? It's all entirely loaded in the X direction. And we have this bar below has a constant width of 35 millimeters and a thickness of 10 millimeters, which automatically tells us our cross-sectional area, right? That we have this rectangular cross-sectional area of 10 by 35 millimeters. Determine the maximum average normal stress in the bar. The maximum average normal stress, which might sound like a counterintuitive statement, but what it means is that in which one of these sections, as the normal force is changing throughout this bar, because every time we have a load, the normal force changes. Kind of like in our shear and moment diagrams, every time we had a load, our shear diagram was changing. Here, every time we introduce a load, whether it's at point A, B, C, D, we're changing what that normal force is in that section. So we want to find which one of these sections has the greatest average normal stress, right? So where is the maximum average normal stress occurring? So here, if we look at this, we have a few basic sections, right? So we can break this off into different free body diagrams. If I look at my first one here at A, this section between A and B, where I have this 12 kilonewton force, and then I break through it, and I have the normal force between A and B, right? Just a super basic free body diagram splitting between A and B. I can find that this normal force between A and B is going to be 12 kilonewtons, right? Again, I mean, it's applying the equilibrium equations, but this we can really just see by inspection that if it's 12 kilonewtons one way, equal and opposite has to be 12 kilonewtons the other way. So this section is pretty straightforward, and then we need to move down past the next loading that we see to capture the next change in normal stress, change in normal force in this beam here. So we can see at B we're loaded with 9 kilonewtons on top and 9 kilonewtons on bottom. So if I cut through this, so section AB, now I'm looking at section BC, really ABC. I'm going to keep everything that was before it, where I have this load, and then I have the cut here at BC. So I have the 9 kilonewtons and the 9 kilonewtons, and then the 12 kilonewtons. So the normal force here coming out, normal force between B and C, if I set up an equilibrium equation, I see that it's going to equal 12 plus 9 kilonewtons. So that's 12 plus 18 is 30. My normal force here in section BC is 30 kilonewtons. And then I look for another load change, and I can see at C we've got the 4 kilonewton and 4 kilonewton loads. They're being applied like here and here on this juncture at C. I'm going to cut through CD. So this is now ABCD. Start with my 12 kilonewtons attached to the ring. Come down, I still have the 9 and 9, and then I come down, and then I have the 4 and 4, now in the opposite direction, 4, 4, and then I have that cut through there. Coming out of that cut, just the normal force. We know there's no shear or moment that we're looking at because this is entirely axially loaded, right? There's only forces in our X direction. So this normal force, CD, is going to be our 12 plus 9 minus 4 minus 4. So that's going to give us 18 kilonewtons to bring this out, to put this in equilibrium, right? So now that we have all of these normal forces, what is our normal stress? What's our average normal stress? Now we could go ahead and calculate our average normal stress for each of these three scenarios, but we really don't need to, because we know that our average normal stress is going to be the normal force over the area. The area is constant for all of these. This is our area for all of them. So really, which one would give us the maximum average normal stress? Our highest normal force, right? Our highest normal force is going to give us our highest normal stress. So this is really the only one that we need to plug in to our equation. So sigma here, our normal stress, is going to be 30 kilonewtons over 35 millimeters times 10 millimeters, right? That's just our normal force we calculated, or our normal force we found over the area calculation. And then we'll have to pay attention to units here a little bit, because if we'll recall, a Pascal is a is a Newton per meter squared. But here we have kilonewtons now over millimeters squared, which we can shortcut if you want. A kilonewton per millimeter squared is going to be a megapascal. We can shortcut it that way, or we can just do the unit conversion calculations. But skipping a couple unit conversion calculation steps, I'm going to say this is, when I punch it into my calculator, 85.7 megapascals. I might have this conversion wrong that I gave you. Now I'm not sure. I know I converted this. I just had Google convert it, to be honest with you. But it's just moving a bunch of zeros around. You know how to do conversions. It's fine. I trust you. Just be aware that this is a pascal. A Newton per meter squared is a pascal. And you have to keep that in mind when you're doing these units and keeping your units and your unit conversion straight. I don't care if you use Google to convert your units. Just understand that your units have to be converted. Let's look at one more example. So in our final example here, I have this 80 kilogram lamp that's supported by rods AB and BC. Each of them have a diameter. AB has a diameter of 10 millimeters. BC has a diameter of 8 millimeters for each of those rods. And we want to find the average normal stress in each one of those rods. Now, this might be looking kind of familiar to you as a problem because we know what our first step is going to have to be, right? We saw a lot of problems that looked like this in statics. Have to start with a free body diagram, right? They don't give us the forces. We have to calculate the force in these rods. And the way we're going to have to do that is with our equilibrium equation, right? So our first step, our favorite step, always, is a free body diagram. Woohoo! You thought you left statics, but in fact, it's always going to come back to haunt you. So here's our free body diagram, each of those two rods, and then the weight of the lamp, right? We can't forget the weight of the lamp. They told us was 80 kilograms, but that's not a weight, right? That's a mass. 80 kilograms, multiply it by 9.81 to get our weight, which works out to 784.8 newtons when I punch that in my calculator. And then, of course, I have my two unknown forces. These are the forces that I need in order to calculate my normal stress. So I have the tension in rod BC, the tension in rod AB. You can label these whatever you like. You can label them force, normal force, whatever. I'm used to calling them tension anytime it's like hanging from something like this. But again, you would call it force 1, force 2, BC, B, whatever you want to call it. As long as you can keep it straight, that's all that matters. So I've got my two forces and my weight, and the relationships here are on BC, we have a 3, 4, 5 triangle. And on AB, we have a 60-degree angle. So this will be a nice little, again, review of statics, a little practice of our statics here to do our equilibrium equations, right? So it's just going to be our sum of forces in the x direction is 0, sum of forces in the y direction is 0. We just go ahead and set up those calculations, plug in, and find those forces. Again, something we should feel pretty comfortable with at this point. So my x component here of TAB, so the tension in AB, times cosine 60. This is pointing in the negative x direction, so that's a negative. Then plus the x component of TBC, EBC, and that relationship is 4/5. So times 4/5, and the W contributes nothing to the x, so that just equals 0. Then I'll set up my y equation here since I can't really solve for anything. So my equilibrium equation in the y direction is going to be my y component of TAB sine 60, and that is in the positive y direction. And then for TBC, I have 3/5, again in the positive y direction, plus 3/5 TBC, and then minus the entirety of W. So minus that W, which is 784.8 newtons. I'm not going to put my units in there, so I don't want to get confused and think that that's a variable. So I'm going to leave that out. I know it's all in newtons, it's all the force. So that equals 0. We go ahead and solve our system of equations, do our algebra here, and we get that the tension in AB, the force through rod AB, is 632. Looks like is what I got on my calculator. Please feel free to double check me. I punch things into the calculator wrong all the time. Especially Google. Sometimes if you don't hit the buttons right on Google, like if you don't hit the enter key, then it'll give you the wrong one when you thought you were done computing. It's quite obnoxious. I've made that mistake a lot. 395.2 newtons is what I get for BC. Excellent. So I have my first ingredient, right, for my average normal stress. My equation is, again, sigma, the normal stress, is the normal force through that body over the cross-sectional area. So I have those forces. I have the forces going through the rods. Now I just need their cross-sectional areas. And thankfully they gave me diameter of 10 millimeters and diameter of 8 millimeters. So diameter immediately tells us it's a circle. For which one? AB is 10 millimeters. So my area for AB is pi d squared over 4. And I can plug that into my calculator. You can convert to meters, or you can wait to do it later if you want to leave it in millimeters squared. Just be conscious of your units. I'm going to go ahead and convert it to meters right now. So that's pi times 0.01 meters squared over 4. So my area AB is about, and I might have a little bit of rounding here, 0.00785 meters squared. And the cross-sectional area for ABC, again, it gave us diameter of 8 millimeters. So pi times 0.008 meters squared over 4 gives me a cross-sectional area. When I punch it in, I got 0.00005 meters squared. So I've got a tension, I've got an area, perfect. Now I can finally do what the problem asked of me and calculate the average normal stress in each rod. Average normal stress in each rod. I'm gonna have my normal stress in AB is going to be this 632.4 newtons over 0.0000785 meters squared, which of course gives me a humongous number, so I'm just going to put it in megapascals. I get about 8.05 megapascals. Again, my answer might be slightly different than what you calculate depending on where you rounded and where I rounded, but we're going to get pretty darn close to the same thing. 395.2 newtons over 0.00005 meters squared. Punch that guy into my calculator, and I get 7.86 megapascals. Boom. Those are average normal stresses in each rod. Pretty straightforward at this point, just to get you familiar with this concept of normal stress and how we use it, how we get there. And we will look at shear stress in our next video.